Hi, everyone. Let's look at another tool for determining convergence, which is to recognize that your series is a geometric series. So first of all, let's recall that a geometric series is something of the form a times r to the k. Typically, we write this from k equals 0 to infinity. And we'll see what to do if the starting index is not 0 later. But this is the definition of a geometric series. An example would be something like the sum from k equals 0 infinity 5 times 1/2 raised to the k. If you have something like this, the important fact, the theorem that we need to use is if you have a setup like this, if you have a k equals 0 to infinity a times r to the k geometric series, then if the absolute value of r is strictly less than 1, this series converges. And in fact, we can tell you what the value is. Its value is a over 1 minus r. Whereas in the other condition, if the absolute value of the common ratio is greater than or equal to 1, this series does not converge. So this is a very powerful theorem if you can recognize what you're looking at is a geometric series. As an example, the sum from k equals 0 to infinity of 7 times 1 over 5 raised to the k. This would look like, first of all, 7 plus 7 times 1/5 plus 7 times 1 over 5 squared, etc. I just keep adding these terms up. So that this is a geometric series. A equals 7 and r equals 1/5. And the important thing here is to look at this r, look at this ratio. The absolute value of 1/5 is less than 1. So by the theorem, what that tells me is this converges, and in fact, you can tell you what the answer is. All right, so this value is actually equal to, that's going to be a, which is 7 value. I think of it as like amplifier. It's what I'm multiplying by over 1 minus r, which is the ratio of consecutive terms I'm adding up. So this is 7 over 1 minus 1/5 is 7 over 4/5, which is 35 over 4. Let's look at another example. What if we had the sum from k equals 0 to infinity of 2 times 3 to the k? Now again, this is a geometric series where my a is equal to 2 and my r is equal to 3. Here, the absolute value of r is greater than or equal to 1. So what does my theorem say if the absolute value of r is greater than or equal to? It says this series does not converge. This series does not converge. That's the basic property that you need. I think it's slightly more complicated. For instance, what if I look at something that kind of looks like a geometric series, actually looks very similar to a geometric series. The exponent is not k. The exponent is some expression involving k. Well, here algebra is going to come to my rescue. I can rewrite this as the sum from k equals 0 infinity of 2 times 1/5 to the k times 1/5 squared. Now I can take this 2 and this 1/5 squared, and I can combine it, and this will become the sum from k equals 0 to infinity 2 over 25 times 1/5 raised to the k. And now we've converted this. This actually is an honest-to-goodness geometric series. So we can apply our test. Here my a is equal to 2 over 25, and my r is equal to 1/5. And the absolute value of 1/5 is less than 1. This series converges. And what does it converge to? Well, it converges to a over 1 minus r, which is 2 over 25 over 1 minus 1/5, be equal to 2 over 25 over 4/5, which 2 over 25 times 5 over 4, which intriguingly, it turns out to be 1/10. So once you have this tool in your toolkit, the thing you want to be able to do, if you can, is take something that looks kind of similar to a geometric series and see if you can rewrite it algebraically so it actually is a geometric series. Another example, let's look at the sum from k equals 0 to infinity of 2 to the k minus 1 over 3 to the k. Again, this is not quite looking like a geometric series, but let's see what we can do. So first, let's work on this exponent so they match. So we could rewrite this as the sum from k equals 0 to infinity 2 to the k times 2 to the negative 1 all over 3 to the k. And now we can pull this 2 to the negative 1 so that it's not part of the expressions involving k because it doesn't need to be. And what's the next thing we could do? Well, look at this 2 to the k over 3 to the k. This becomes k equals 0, infinity, 2 to the negative 1, and I can rewrite this as 2/3 raised to the k. So this becomes the sum from k equals 0 to infinity, and this 2 to the negative 1 is 1/2, so this becomes 1/2 times 2/3 to the k. Now I recognize this as a geometric series. And my a is equal to 1/2, and my r is equal to 2/3, and the absolute value of that 2/3 is less than 1. So I can apply the formula and say that this is equal to 1/2 over 1 minus 2/3, which is 1/2 over 1/3, which is 1/2 times 3 over 1, which final answer is 3/2. Now, if somebody had given you this awesome looking expression this time last week, you might have said, well, it's like alien hieroglyphics. Now you actually understand what this means, and you can come up with an understanding of how this works, which is amazing to me. Absolutely amazing. One more thing let's look at that's just a basic structural variation, and that is, what if this doesn't start at 0? So what if I have the sum from k equals 4 to infinity of 3 over 7 raised to the k? There are two different things I can do here, and I'm going to show you both of them. So the first is I could do a substitution on the variable so that it does start. And if I want this to start at 0, I could say let t equals k minus 4. So when k equals 4, t is equal to 0, and k is equal to infinity, t is equal to infinity. I'm going to plug these in, and this would become the sum from t equals 0 to infinity. Now, let's look at this relationship. T is equal to k minus 4, so k is equal to t plus 4. So this becomes 3/7 to the t plus 4. And now I'm in a situation similar to the one I was in before. The exponents don't match, but I can work around that using algebra. So this would be equal to the sum from t equals 0 to infinity of 3/7 to the t times 3/7 to the 4th. And that becomes, I'm just going to rewrite this so it looks more like the form that we were used to. And looking at this, I say, wait a minute, this is a geometric series with a equals 3/7 raised to the 4th, and r is equal to 3/7. So this converges, and this value is equal to 3/7 to the 4th over 1 minus 3/7. I could simplify that if I wanted to, but for right now, I'm just going to call that my final answer. The key is sometimes things don't look exactly like the geometric series format that you're used to, and that's okay. You just work around it by rewriting it in a form that makes sense. And in this case, we did a substitution of variables so that our index started at 0 instead of at 4. In a different video, I'll tell you a different way of doing that. Right now, this substitution trick gets us the answer, so let's stop there.